Okay. So we are here. We just finished talking about the our star, the sun, and it became pretty apparent that the sun's actually, we were grateful for it because this is how we're still alive. But the sun emits a lot of visible light, but it's much more interesting in other wavelengths. So now it's time to start talking really seriously about other wavelengths of light. So we'll kind of go back a little bit. And we skipped this the first time through because 3 chapters of physics would have been a bit much. So we'll go back and talk about Spectra, which is chapter 5, and then skip back ahead and start talking about stars and the sun, which are 10 and 11. We'll start exercise 6 today, which has to do with spectra and making light and classifying light-emitting things. And then by Friday, we'll be knee-deep in this thing called the HR diagram, which is really like, if you took this class in 1840 or something like that, the HR diagram, maybe 1880, this would be like the thing that you spent weeks and weeks learning how to use in exquisite detail and precision. So 2 things coming up. Midterm, we'll do that after we finish the HR diagram and get to star lifetime. So that'll probably be not next Friday, but the Monday after it. I think the tentative date on the course calendar is looking like that's pretty reasonable. And then secondly, it's kind of hard this quarter because of scheduling, but I can get time at the UW's fancy digital planetarium. Probably the best time to do that would be like the second to last week of class and either a Monday or a Tuesday. So we'll have like a straw poll vote. How many people would be interested in going to the planetarium? Okay. How many people have a strong preference Monday versus Tuesday? Is Monday better? Be like 3 p.m. to 5 p.m. or something like that. How many people say Monday, strong preference? Tuesday, strong preference. Totally ambivalent, no preference. Okay. Maybe I'll make a real poll out of it and put it on Canvas, since it seems to be kind of split. But if people are interested, I'll definitely do it. It's everybody who's went actually has found it to be pretty entertaining and useful because the final exam will be coming up. Okay, good. Because it's a bit obscure, I think today we should review the physics and the anatomy, like what happens if you cut the sun in half and look at the layers, and then really stop and talk about the physics of light and what's the same about light and different, and then we'll start in on star classification. And there's some history in this too. If we wipe the slate clean and you guys were to, all the books burn and you have to reconstruct a theory of astronomy, you never would have classified stars using this classification scheme. So there's some history in it, and it's not entirely just like intuitive and sensible. So we have to learn a bit of history, and there's a mnemonic, kind of like the biology mnemonic about kingdom, phylum, class, order, family, genus, species. So this is our picture of the sun, at least as much detail as we need to know, is that it's mostly hydrogen, about a quarter helium, 2% is heavier stuff. If we sat there and we let a billion years tick off, this would change a little bit because what's actually powering the sun, the conversion of hydrogen into helium. So, come back in a bit and it'll be 73% hydrogen, 25% helium. And this is all happening in the core. So within the middle, like maybe 10% of the mass, that's where fusion happens at 16 million degrees Kelvin and a density about 10 times that of lead. The next layer is the so-called radiation zone, where these evil gamma rays, the most energetic of all the possible photons, which are created in fusion, bounce around and they interact with matter, and matter is still really, really dense, and it's plasma, so these aren't atoms. They're a sea of protons and neutrons, and protons combined with neutrons and electrons that absorb the light and spit the light back out, and absorb the light and spit the light back out, and it takes on the order of 1 million years to fight its way through the radiation zone. So at the edge of the radiation zone, maybe you're down to like a balmy 1,000,000 degrees Kelvin, where matter can start having bulk transport, so hot gas will bubble out towards the edge of the sun, where it will cool off, and then it will sink because cooler stuff is denser. Just like circulation currents in the ocean and the atmosphere do the same thing. These would be plasma circulation currents in the so-called convection zones. This is the process of convection. And by the edge of the convection zone, where you get to what we'll call the surface of the sun, it's about 5,800 degrees above absolute zero. So warm day on Earth is about 310 degrees above absolute zero. So a lot hotter. So the important part, even though by mass it's almost negligible, like you think about the photosphere as maybe like the skin of an onion, like the peel that nobody eats, the first thing, that really papery stuff that you get rid of. So it's really the photosphere. And we talk about this a lot because when somebody says, this is the temperature of a star, they're talking about the temperature of the photosphere. And when they talk about the color of the star, they're talking about the color of the photosphere. It could be like much, much hotter inside, certainly. And then the only thing I want you guys to know about the atmosphere is it's really cool and not totally understood. In particular, there's this weird magic trick where this material and the temperature has managed to fight its way from 16 million down to 5,800 degrees Kelvin. Then all of a sudden it jumps back up to 1 million through some sort of weird effect where the particles are being accelerated by magnetic fields or something like that. So it's a goofy place. Yeah. Yes, the fate of the sun and what happens when it swells up as a red giant and will eventually eat the Earth in like 4 billion years absolutely has to do with the slow ticking away of the... if you think about it, like hydrogen is what a star has in its gas tank, and it's slowly burning through its gas. And why it swells up when it finishes burning is a totally different and, rather complicated question, but we'll deal with that after in the midterm when we talk about star death. So yeah, totally. At the end of... this is how much we have left. So we have quite a bit to burn, actually. It's fine. So another 4 billion years of nuclear fuel. Yeah?
This heavier stuff.
Yes. Yeah, there is... so the heavier stuff in our sun was given to us from the fact that we're actually a recycled solar system. So this entire, everything around us, I know by virtue of there being like carbon and things and iron, we're actually recycled. We were from a previous heavier star than our star. So the sun isn't making that 2% heavier stuff. And our sun actually doesn't have enough mass and power to get beyond carbon. So the heavier stuff is stuff that was kind of gifted to it at the formation of the solar system. It's not making it. And there was actually a really strong divide in between so-called low-mass stars that don't make heavier stuff and high-mass stars which do make heavier stuff. And we're, believe it or not, 2 times 10 to the 30th kilograms. We're a low-mass star. But that's also, we'll get to that, the full story, in when we talk about star death. So like split the two groups, and they're the wimpy guys like our sun, which never make heavy stuff, and then figure out where uranium and gold come from. And it's definitely not something like our sun. Good. Other questions? Well, I feel like my answer was that was wait a week and a half. True. Okay, and then there's this, the important part about the solar atmosphere and weather, and the reason that once every decade or so, the sun freaks out and spits off enough energy that you can see the northern lights at pretty low latitudes, is it's not solid. So when we talk about the rotation rate of the sun, it actually depends on where you're standing, and it takes about a month to orbit the pole, and it takes less time, in fact 25 or so days, to orbit at the equator, which would be like a really, really obscure fact of astronomy trivia were it not for the fact that this 2 times 10 to the 30th kilograms of plasma has a huge magnetic field, and magnetic field lines do not break. They only warp and they twist. And because of this differential rate of rotation, they actually get tangled. And after about a year or so of tangling, it's noticeable. And after 10 years or so of tangling, it's completely tangled. And every once in a while, the sun freaks out and has to untangle its magnetic fields. And the way that it does that is by things like this. So what you're seeing is, this is not a visible light image. This is an X-ray image. of the sun untangling its magnetic fields, and all these charged particles, the plasma, actually follow along magnetic fields like they do in the northern and the southern lights. This is the sun's own like kind of intrinsic version of that, because it's trying to untangle a magnetic field. And in fact, when you see sunspots, what you're seeing is the entry point or the exit point of the, it doesn't make a difference, the entry and or exit point of the magnetic fields as it leaves and returns to the sun. And they tend to come in pairs, in fact. As far as, so the problem is you would need to get like the resolution good enough to actually observe the disk of the star. Yeah. Yeah, when you see, and this is a big thing that, you can make it through an entire 5-credit introductory astronomy course and not realize is that when you see a picture of a star that's like 2 by 2 pixels, it just means that it's saturated 2 by 2 pixels, or the atmosphere smeared its light out by 2 by 2 pixels. You cannot image, like spatially resolve the disk of a star, even the closest star. Just the actual size is so small that you really can't see it. There's evidence of solar weather, but it comes from just looking at the total light of stars. And if the total light of stars is like bouncing all over the place, then it's freaking out like this. So particularly, there are things called flare stars that actually, they have serious solar weather, and they have, their output will like almost double in power over the course of a couple of hours, just like kind of freak out and emit some flares. They're actually people say things like the mouse that roared. They're usually like really, really low mass stars, and they freak out. So there's a lot of indirect evidence, absolutely, but it would be hard to get a picture like this. Possible to get a picture like that of another star. Other questions? Okay. So these are some of those in pairs. You can just see them. They kind of match. So this would be an incredible big loop of magnetic field line with all sorts of stuff going across it. Okay. And this is partly historical records. So people were observing sunspots, in some capacity since the days of Galileo. I think this record comes from proxies for solar weather, but there's absolutely an 11-year cycle and some other stuff going on. There seems to be this incredible low point in the sun's solar storm career in between 1650 and 1700. Anybody know what was going on kind of climate-wise? Like super history nerd in between 1650 and 1700? Yeah, it was a little ice age. And in fact, in in Newton's day, and in fact, even earlier, it was a little bit suppressed too. So this is not modern climate change, but you hear these stories of people in like Elizabethan and Jacobean England where the River Thames would like freeze over 10 feet thick, and people would like go ice skating in London. People do not go ice skating in London anymore. So you see old paintings, and it was apparently like little ice age. It really was true, and that seems to be correlated with a downtick in solar activity. So maybe sunspots were suppressed because the solar activity was suppressed for some reason that people don't quite understand. But apparently there's a 300-year super cycle, and we're kind of gearing up to getting back to this actually. So that would be nice for me at least. Okay, and then we watched a whole bunch of pretty pictures of non-visible light of solar storms freaking out. This is absolutely not what the sun looks like. It's not like somebody took a piece of blue gauze and put it over the sun. This is actually light that the human eye does not detect naturally, and this is where we are now. So non-visible light. So this is the entire electromagnetic spectrum, or at least the parts that we'll talk about. These are really artificial, and they mean a lot to humans. Light itself does not care about these designations. It's not like gamma rays pass X-rays and say like, haha, you're an X-ray or something like that. So these are totally artificial, and they have to do with how human beings use light, in particular this tiny little sliver there, and this is a complete cartoon. So the wavelength of gamma rays would be 10 to the minus 15 meters. So take a meter stick, cut it into 1 million pieces, take one of those pieces, cut that into 1 million pieces, take one of those pieces, cut that into 1,000 pieces, and you get one of those. Whereas microwave and radio wave, that would be like the meter stick itself. So this is complete cartoon. And it took people a while to realize what was going on because we have these biological things that are really good at detecting visible light and nothing else. So the connection in between why certain things feel hot, or in fact, you can break up a prism and put a thermometer past red. This is how it was first done. Somebody just noticed that their thermometer, which was hanging out to the red part of the spectrum, actually started going up. So it was absorbing some radiation that they just couldn't see. And then radio waves, we use them to communicate, so we break those off. Ultraviolet, we use them to get tans, so we break those off. X-rays, people didn't really realize that was light until, like 1910 or something. So 1905, so shockingly late. But this is totally artificial. All it is electromagnetic radiation, and we want all of it now. So this is a solar storm in UV. This is the same solar storm in X-ray. Wow, we just got a lot more information. Because the coronagraph, so this little disk which is blocking out most of the light of the sun, you never look at the sun with eyes and see this loop that's about the same, if not 1.5 solar diameters flying off of it. If you had X-ray eyes, you would absolutely see something like this once every couple of months or so. Oh, I don't know. Mm-hmm. Yeah, I don't know that this is the same solar storm depicted in both pictures, because it's been so long since I ripped this off of the textbook. And I don't think they told you. So I would imagine that this is probably not the same solar storm, because I think the loop that you see in UV would also be apparent in X-ray as well. Yeah. Okay. So this is the electromagnetic spectrum. Remember, that's a cartoon. You guys are now on the hook for knowing the parts of the electromagnetic spectrum and who's got a longer wavelength than whom. But really, it's all the same thing. And if I have a packet of radio waves, radio light, and I have a packet of gamma rays and X-rays and visible light, and I start this race where I just shine my X-ray flashlight and my laser pointer, which is red, and my beam of infrared radiation, which is actually coming off of me at all times, and poke a hole in the door of my microwave, and I set them in a race against each other through empty space. They all move at the speed of light. It's the speed of light, which is really nice because you don't want to see images like stretched out over the sky because some light travels more slowly than others. And it would be. So light can be dispersive. That's the reason a prism works. But in general, it's not, and we're really happy for that because the world would smear out into this like psychedelic pastiche. So it's the same C and E equals mc squared, but they have different parts, and we'll use them, this radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, just to kind of indicate the energy of what's going on. Because it turns out that stuff that's more energetic is shorter wavelength, and stuff that's less energetic is longer wavelength. And specifically within this cartoon, you'll realize why building detectors that are able to observe non-visible light is amazing. Because even though eyes work pretty well, there are a couple of problems with them. They only collect light for 1/10 of a second. That's an issue. Photography fixed that. But even still, we're talking about half an order of magnitude. So from about 470 billionths to about 790 billionths of a meter. This should be condensed. This is the most pathetically small sliver of electromagnetic spectrum. And we get half an order of magnitude, so half an order of a factor of 10. And there are easily like 18 more out there. So, Again, if anybody hassles you about how perfect the eye is, you know that it's wrong now. Okay. So the thing that we'll do a little bit more and over the course of the entire second half of the quarter is you'll end up with some intuition for what different wavelengths really mean. So the cosmic microwave background radiation, for instance, these are long wavelengths. So it indicates that this thing doesn't have a lot of energy left in it. So you guys know what the cosmic microwave background radiation is from? Yeah, it seems like the Big Bang is a pretty energetic event. Why am I saying microwaves are wimpy? Well, when was the Big Bang? Yeah, so 13.7 billion years of cooling down has turned the most energetic explosion in the universe into microwaves. So their wavelength is about this big, a couple of centimeters. There are things called radio galaxies, which means that there's something that's pretty non-energetic happening. So pretty, in this case, I think it's plasma and electrons falling into the center. Jupiter, actually, because it's got a lot of wind and gas and a strong magnetic field, Jupiter kind of sings in radio waves. This is really low energy stuff. If you were to get infrared goggles or an infrared telescope, or if you were a snake, they actually see an infrared. Snake astronomers actually see the planets glowing, and us for that matter. That's kind of how they make a living. In infrared, so this is what we would call our blackbody spectrum. So that's about like the warmth of a person would be making infrared light too. Stars emit visible light. That's why they're kind of our favorite historical astronomical objects. After a while, you start thinking that honestly, like stellar astronomy is just one part of it. It's just because we see them in their visible light, we tend to overemphasize them. So you get into X-rays and gamma rays, and now you're talking about sort of energetic, fast-moving, crazy events like material being pulled off of a star and sucked into the drain of a black hole, or a black hole being formed itself, gamma ray bursts. If you have neutron stars, the cores of dead stars, so you take the entire mass of the sun and compress it into something about the size of Seattle, that would probably emit X-rays and gamma rays. So it's more energy, less energy, shorter wavelength, longer wavelength. But again, they all travel at the speed of light, and if you just figure out the engineering problem of actually detecting the light, you get all of this new information. So before we were, and now 20th century, we get all this stuff, which is really nice. Okay. So this comes at a price of having to employ artists. It's not true, actually. The Hubble Space Telescope in particular, there are people, their job is to make and present this information, actually. And they do an amazing job of like dreaming up a color palette and making it consistent and making it tell the story of what's actually going on in this stuff. So we only see visible light, so if somebody wants to tell you what's going on in X-ray or infrared, they actually have to kind of like choose a way of doing that and paint by numbers. So this is not what would happen if you were to look at the star-forming cloud in Orion's belt. This is a Hubble image. You can tell it's got the missing Tetris piece. Somebody painted this, and each color means something different. So these would be oxygen absorption lines and some infrared light, and somebody has to furnish a key to tell you what they're really saying. So if you look at the Eskimo Nebula, that's really what it's called. This is the furry hood, right? You would not see this. This is a halo of X-rays, soft X-rays from the Chandra telescope, and you would have to have the people at the Chandra telescope project publish their key and say that this is really energetic X-rays and less energetic X-rays and stuff like that. So if I don't say it and I forget, at this point onwards, if something doesn't look legit, like you really wouldn't imagine seeing that out in the heavens, you're requested to say like what part of the spectrum is that, because sometimes I forget, or I think you guys recognize the Chandra color palette after a couple of weeks or something. And then even worse things happen is people make these so-called composite images where they try to map on stuff that you can't see with the human eye to a background of stuff that you could. So this is a background of visible light stars, so it's just like a normal star field, but then they observed it with infrared and X-ray and then painted those things on separately. So it's visible light, and the green-red stuff is, I think that's the infrared, and then the blue is X-ray. And what they're trying to tell you is that something really energetic is happening here, and then something, there's a halo of cooler stuff. So maybe this is a really hot planetary nebula from a low-mass star that just blew up. Because something really energetic is happening if I see X-rays. And maybe the infrared is from a less energetic earlier part of the pre-explosion or something. So let's try this. Now that we have all of the parts of the electromagnetic spectrum, let's see what it tells us about our star and the moon. And this is the interesting one, actually, I think. We get the lights. So what do you think is going on with the sun? And I think these are our contemporary images, aside from this picture of the moon, is the moon in full phase. This is not the moon in full phase. So this one doesn't match the other ones, but everything else I think is taken at the same time. Okay. So the X-ray tells me that something really energetic is happening where I see more X-rays. I presume that brighter means more X-rays. And then ultraviolet, I see the same storm. Visible light, I guess that's in high contrast. Infrared. This is kind of interesting. It looks like the energetic X-rays are associated with less heat, but that's what we saw in sunspots, is that sunspots look dark. They emit less visible light, but they apparently emit more X-ray and ultraviolet light. And then in radio, we actually have a pretty radio quiet star, but apparently the sunspots also emit radio waves. Good. What do these images tell me about the moon? So X-ray, ultraviolet, visible, infrared, radio. So there's a lot in there. It's the first part, X-rays. So let's do that first. Okay, good. So the moon doesn't seem to be producing its own X-rays. I see some X-rays there, though. What's that, do you suppose? Yes. Yeah. In fact, what's happening is the sun is producing really energetic particles in its solar wind, and they're actually coming in and they're smacking into the moon. So the moon is basically acting like a big particle physics experiment.
Right.
Yeah, and this is actually the origin of the moon's really wimpy atmosphere. So in fact, this is one of the first X-ray things that people thought that they were going to see. Because X-ray astronomy, people actually didn't think there was going to be anything interesting for a while because X-rays have so much energy. They're their own worst enemy is that they hit matter and then they ionize whatever they hit. They disappear. So in fact, this is solar wind coming and bashing into the moon and actually causing X-rays. You can think about it as like sparks from the solar wind impacting on the moon itself. They're not reflected X-rays directly from the sun. What they are is solar wind smashing into the moon. And you can see a little bit of the same thing in radio too there. Yeah, good. What about infrared? Are there warmer and colder parts of the moon? Yeah, it's kind of hard to see in the back, I think. But again, if we're presuming that their color palette means that brighter means more of that light, I definitely see a really bright spot there. Is there some feature that it correlates to on the visible light or any of the other images?
Lighter on lighter spot?
Yeah.
Lighter spots.
So this stuff, the lava plains from This is kind of hard to see, but I'll bring up a brighter picture of the moon, and it'll immediately pop out at you. But good, yeah, it looks like the moon is cooler in the lava plains. The lava plains have not been, the fact that they're kind of unmarred means that they haven't been repaved by impacts, and they're from when the moon itself was molten, which is like 4 billion, 3.9 billion years ago. So let's look at this, and let me bring up, actually, maybe I can just do this. So what do you notice right there? That is a big honkin' crater. What do you notice right here? I don't know if that's Tycho. Could be. That's the giant one, right? Yeah. It could well be. So this is actually where the crater, maybe Tycho, is. Where's that bright spot? Do you think that the moon is still warm from a billion-year-old impact? Apparently so. But this is not stuff that you would see just with visible light. So you actually get a lot more information, even from something like as old and familiar as the moon. Apparently the moon is a giant particle physics experiment. It's a pretty recent crater. I don't know when it is, but certainly more than a billion years old. So ray craters are pretty young. But this crater is still warm from being smashed by an impactor, at least a billion years ago. So this is really useful. Right? So provided you give me the technology to make telescopes in different wavelengths of light, this is great. Okay, so let's try things that are less familiar. Pick some random thing. This is Messier 17, 20, and you'll figure out what the Messier catalog is by the end of the quarter. And then this thing, the Tarantula Nebula. So what can you tell me about any of these things and why? So now you're truly an astronomer in the fact that you don't know a priori. You know what the moon is, and you know that it was hit by craters. But I don't know if you guys have any prior knowledge of what's going on with like emission nebula and the Trifid Nebula. So. Based on, so maybe you could look at temperature in some sense. So the Trifid Nebula has, they both have some spattering of radio. They seem to have some central core of X-rays. If you take these things really seriously and you can do an apples-to-apples comparison, it certainly looks like the Trifid Nebula has less radio going on, so you could maybe argue that, yeah. Anything else? Sneaky though, because this is a Spitzer image and that's a 2-mass image. So you'd have to go and talk to the Spitzer people and get their key, and then the 2-mass people and get their key, so it's a little bit annoying, but yeah, comparing between from nebula to nebula will be hard, provided if they're not the same catalog. So, but overall, what can you tell about this thing? So, in particular, when I look at this invisible light, what do I see? Certainly in this. So these like lanes of, big diffuse, and then I see these. Either there's no light there, or maybe my light's being absorbed. Is it immediately obvious that there's some like really energetic thing sitting at the center of this from the visible image? What about that? Like a cloud, right? So what happens when you look at the X-ray images, though? What do each of these have? There's something, like they each have some sort of candy core, right? I don't know what that is, but the cloud may have obscured that. Okay, and then even weirder is if you look at the Tarantula Nebula, in ultraviolet it seems to have a very energetic ultraviolet source here. Where does it seem to have a really energetic X-ray source? There, so they're not necessarily the same thing. Good. And it turns out the emission nebula is a cloud of gas which is being heated up by something, and so it shines like a neon light, the whole thing, light year across neon light. And the Trifid Nebula, I think, is a star-forming cloud, and this is dust and gas lanes, and there's a really, really single bright star in the middle. So, but we'll get there. But as long as you start thinking in terms of different wavelengths of light, and X-rays mean high energy, radio waves not so much, and the total, every astronomer's least favorite thing, unless you actually study dust, will be this stuff. These dark lanes come from dust. Good. Okay. So put a little bit of terminology on this stuff. So there's a spectrum. What an object spectrum is how much of each type of light. So this is actually, in principle, pretty hard to describe. So what people resort to are these diagrams called intensity diagrams. But what it would really be is, okay, I've got a lot of blue light, and I've got not a lot of green light, and then I've got not so much red light, and maybe I have some way of figuring out how much ultraviolet and infrared and radio I have. And I publish that and tell somebody else. So that's the so-called spectrum. Take the total light from the source, break it up with a prism, some sense of the word, and then send it to my friend in some sort of diagrammatic way. So, a question about plain old ordinary prisms. So I have white light coming into a prism. It came from the sun. Now that you guys know more about the sun, do you think that there's light there and there's light there? Yes. In fact, this is really how infrared light was discovered. I think it was Christian Huygens just left a thermometer there and started noticing it was going up. It was like, what the hell? His experiment, I think he was trying to do exactly that. He was trying to make a scientific spectrum of sunlight where if you put a bunch of thermometers across this, you would get some sense of like how much energy each part of the spectrum has, and you can send that graph to somebody. So absolutely. So there's infrared and there's X-rays and stuff like that. And we'll do this. So we'll represent those as so-called intensity diagrams. One is because it's easier just to plot like the total amount of light at whatever wavelength versus wavelength. Secondly, I don't care what art supply store you go to. I don't think that you guys have infrared or ultraviolet colored pencils, so this won't work. So really what I want to do is if there's more light of a particular type, I indicate higher on the intensity graph, and less light of a particular type, I go down, right? And this works across all parts of the spectrum. This is nice. And we'll do this. So from here on out, no more spectra is represented by strips of rainbow, because there's more to it than the rainbow. We'll use these things, intensity diagrams. Okay. So any questions about spectra? We will stop and I will show you types of spectra. And yeah. The prism does the thing that I told you can't do. The prism allows light to be dispersive. And what happens is blue light travels faster through the prism or slower through the prism than red light, for instance. And other materials would do other things. So it's dispersive at optical wavelengths. In truth, everything but vacuum is a little bit dispersive, but you don't really notice it. In fact, if you go from air to water, light slows down by about 30%. So, yeah.
That it was like that kind of thing.
So the question is basically like, what on earth would I mean if I wasn't just joking about having an ultraviolet pencil? That's a good question. So to me, as like a physicist, if I went to the art store and they were selling ultraviolet pencils, what I would hope and believe that meant, and I would sue them if it wasn't true, is that, so what does a red-colored pencil actually do? Reflects the red light, exactly right, and nothing else. So there would be this thing that looks like transparent or maybe white or something like that, and I would believe that what it would do is if I shaded a piece of paper with it, that patch would reflect ultraviolet light. So you're still left in the quandary that your ultraviolet pencil, you really have to Yeah, people would have to be taking your word for it until you brought up, you actually went to somewhere, found a snake that is willing to give you the answer, or an ultraviolet detector of some type, and pulled it up to the patch of pencil scribbling. So, yeah, what that would mean is a pencil that reflects that particular wavelength of light, which I think I think a silver pencil would probably do all of that stuff, because silver reflects just about everything. So it's the all wavelength of light pencil. Yeah. But I think this is easier. So unless you guys find some ultraviolet pencils and manage to convince me that they actually do what they say. Any other spectrum questions? Yeah. No. Dark matter does not absorb light. Dark matter does not emit light. Dark matter does not reflect or focus or change the trajectory of light except through its gravitational influence. So it's really weird because it's like Marvel comic book stuff, is if I gave you 2 kilograms of dark matter, it would feel like 2 kilograms of stuff. Unfortunately, you have to interact with it with electromagnetic forces, which is really the force of touch, but presumably you were holding it in some container. It would be really heavy, but it would be completely invisible because light would just pass right through it, and it doesn't make any of its own. But yeah, this is why people don't believe it's real. Dark matter does not, and dark energy does not. So the two things that, even though they have completely different scales of influence and they're very drastically differently behaved. The two great cosmic riddles of dark matter and dark energy neither absorb nor emit nor interact with light except through their gravitational influence. So they have mass, but they have no interest in electromagnetic fields. Electromagnetic radiation passes right through them. It's weird. And it's unclear as to whether or not, in particular in the case of dark energy, if it's not just like some figment of like a bad mathematical law or something like that, that people are just saying like, no, it's real stuff. So just like bad math. So that's possible. So maybe an analogy would be, let's say that you took your thermometer, like a normal mercury thermometer that you might use to put under your tongue if you're sick or something like that, and then you just like went to the surface of the sun, and then you concluded that the surface of the sun was 105 degrees, because that's the top of your mercury thermometer reading, is that it's like kind of the mathematical equivalent is we have a theory and then we use it when it shouldn't be used and therefore conclude the wrong thing. So that's the idea possibly behind dark energy, although that parameter space is kind of shrinking every day. There's like more and more energy that dark energy is real stuff. That'll be kind of it's a weird way to end a class, but like we know nothing and then get out of here. So, everything we've learned is a lie. But yeah, we'll get there. Good. Other questions? Okay. So now that we know stuff about spectra, and we know stuff about our sun, and all wavelengths of light are available to us in the 21st century, we're going to pull Newton's trick where we pretend that what we observe locally, which is to say our sun, and we cut it in half, and we observe its properties and know a lot about it, and we now know stuff about light, is we will presume that the laws of physics are the same for all of these other stars and do our best to understand why they're the same and why they're different. And right off the bat, there's one overwhelming weird thing that happens when I look at the spectra, which is to say the colors of these stars. How do they differ from our sun, just quite obviously? Red, blue, white, yeah, they seem to be no green stars, but aside from that, any part of the visible light spectrum, they seem to have predominance of light in that part of the spectrum. So why on earth is that the case? Any guesses? Age? Temperature? Stuff inside? Yeah. All excellent suggestions which have been historically tested at some point or another. And really this is it. We've got like this nice kind of jaundicey yellow sun. Why is it yellow and why is it not blue or white? And maybe the first and most popular theory, I don't know, we could do poll. How many people think, I think the three were that it's something to do with the light itself. Maybe it's traveled for a longer distance. So light itself changes color after being emitted. Any takers on that? If the thing is absolutely there's a cosmological redshift, quote unquote, but you have to be galaxy far to start having that happen. So the people actually say that Hubble has completed its job because it's seen things that are so far away that they've been made so red that they're infrared and Hubble's detector can't detect them. But for close stars, you don't have to worry too much about that. Okay, what about composition? So blue stars are blue because they have chromium in them or something, and white stars are white because they have titanium oxide. Okay. Couple takers. How many people say temperature? An equal number of takers. Good. So that's kind of what I presume. So I think historically the composition idea was kicked around for a really long time because that's kind of how things work on Earth. Is you want to make paint of a certain color, you have to go and find the correct. You want to make green paint, you got to find some copper or something like that. You want to make white paint, you got to get titanium oxide. Believe it or not, titanium oxide is found in stars. But you can disprove that with a trip to the smelting factory. So I will do this, and you have to realize that stellar surfaces are pretty hot, and something is, you lose some information when you get something hot enough. And you could totally answer this question if these are all room temperature metals, but they're not. And I will give anybody $1,000 if they correctly identify the 4 different metals depicted in this picture. It'd be so easy if they were like at 300 degrees Kelvin, right? Room temperature. Which one?
Oh.
Yeah, it's hard, right? So what are you really seeing when you look at these 4 metals? Do you see their chemical composition at all? No. What are you actually seeing? You're seeing that they're red hot. And this is uniquely associated with the temperature. And actually, a very nice way is that this is actually from a smelting manual. So forgive the fact that it's in Fahrenheit. We'll not do anything in Fahrenheit aside from look at this picture in this class. Is that it doesn't matter what the metal is. So this manual tells you that if it's this hot, it's 1200 degrees Fahrenheit. If it's that yellow hot, it's 2500 degrees Fahrenheit. And there is absolutely nothing about the composition that you can tell. It's red hot has some temperature, white hot has some temperature, brown hot has some temperature. If on the final exam you had to touch one side or the other side of this bar, which one would you choose to touch? Right, because you know it's cooler, right? Do you know what this bar is made out of? No, it could be tungsten, it could be iron, it could be steel, it could be copper or something like that. So you really don't know just based on the temperature. So this is one of the reasons it's called this actually is because you're kind of agnostic as to what the stuff is made out of. So this is a nail, it's probably iron, but I don't really need to know that. And they're passing a current through it, and eventually you're going to see that it's red hot, yellow hot, and then by the time it gets to white hot, it actually burns through, I think. So I want you to watch that again, but then really start thinking about what you're seeing outside of the kind of, I don't know, human eyeball visible light chauvinism, where there's more stuff going on than you can see. So what you're really doing is you just have your visible light window on, like a lot more electromagnetic stuff going on. And when this nail is like 800 degrees or so, it's actually emitting a tremendous amount of infrared light. And by the time it's about to break, it's actually even emitting some ultraviolet light. So what you see and the overall color that you associate with it is really just the part of the visible light spectrum it intersects. But even when it's pretty cool, in fact, even when it's room temperature, you'll actually, this nail is emitting light. It's just light of a much longer wavelength, as it turns out. So you can see it. It's actually emitting now some red, but tons of infrared light. If I had infrared goggles, this would be blowing up. And then as it starts emitting equal amounts of red, blue, and yellow, it starts to look whitish, and this is the part where it starts freaking out, snaps. And then it cools back down. So we even got some ultraviolet light out of this, in fact. So the mu, this is nanometers, so that's a billionth of a meter. So this is the wavelength of light that people see, 700 billionths of a meter to like 400 or so. Crazy small. So this is what's called an object's Blackbody spectrum, and I don't know exactly this is what people were thinking, but it's a really good mnemonic in the sense that you are totally agnostic as to what this thing is made out of. It's just at a certain temperature, so it's emitting a certain type of light. So it could be, again, tungsten or silver or iron. You have no idea. All you know is you look at this thing and you can uniquely associate color with temperature. So Blackbody spectrum. And all things do this. We're doing this right now. We're just doing it in the infrared. Okay. So this is not like a real stellar spectrum, but this is kind of a cartoon of a stellar spectrum. And notice that it's in logarithmic units, so times 10 times 10 times 10 times 10 times 10 times 10. This is kind of what some stars might look like, a little bit cartoonified, and then a human for comparison. So we're at a temperature. Anything at any temperature has a Blackbody spectrum associated with that temperature. at 310 degrees Kelvin. Ours is completely in the infrared, so that's why you don't see humans glowing and glowing a little bit more when they have a fever. For a 3000 degree Kelvin star, the Blackbody spectrum looks like this. So not a lot of infrared light at longer wavelengths, lots of infrared light at very short infrared wavelengths, a little bit of ultraviolet. But the important part, and the part that lets you see what color the star is there's much more red visible light than blue visible light. So again, lots of other stuff going on, but as far as us looking at it, more red than blue visible light. So what color does the star look like overall? Red. So this one, a little bit hotter, that's the sun. The sun's blackbody spectrum looks like this. Sun's pouring out infrared light, lots of ultraviolet. This is why we all get sunburned, the part that makes it through our atmosphere. And basically it emits just as much red and blue and yellow, so it kind of looks yellowy. Turn the temperature of a star up to 15,000 degrees Kelvin. So you guys know that there was red hot and then yellow hot and white hot. Apparently, if you keep going to 12,000 degrees, you start getting into blue hot. It's true. So this thing has more blue light than red light. So overall, this star, to our poor, measly, visible light detecting eyes, looks what color? Blue. Yeah. But there's a whole circus of electromagnetic radiation coming off of this thing. Good. So now we can start doing a remarkable amount of stellar astrophysics just by looking at pretty colors. Tell me what you can about this star. So about what temperature? It's a cooler star, yeah. And I don't know, if you were to guess a temperature, what do you think it might be? 3,000 sounds good. Specifically, that 3,000 or 3,500 is the temperature of what? Photosphere, right? So that weird onion skin layer, and who knows what's going on in the center. Okay, so what about this? What about this kind of blue-white one? Hotter, much hotter. So depending on how seriously you take this color, I don't know, maybe something in the 10 to 20,000 range. Okay, what about something a little bit harder? So this one that's more orange than, well, I'll just leave it at that. So this kind of orangey one. 43, I think, is a good number. Yeah, definitely cooler than our sun, but hotter than this very red 3,000 degree Kelvin star. Okay, so at this point, in another course, you'd wait until the end, but just intrigue you guys with this question is, what if there were 1,000 degree Kelvin stars out there? Lots of them. Absolutely not. So for tens of thousands of years of human history, there actually are 10,000 or 1,000 degree Kelvin stars out there, and they are invisible, and they're just kind of floating through the cosmos, and you can't see them without infrared detectors. So in fact, if you take this field and you double the number of objects in it, you have about the number of so-called brown dwarfs. Yeah. The factor of the factor of 2 that you get by including the brown dwarfs definitely means there's a lot more light coming in and hitting us. But the evil genius of Olber's paradox is that it's infinity. So every direction that you pick, there needs to be an infinite number of stars all emitting light in any wavelength that you could possibly imagine. So it's kind of weird. It's like infinity is, people literally go insane thinking about it, because what Olber's paradox would tell you is that not only is there a star in any direction you pick, there's a particular type of star in any direction you pick. If you want a variable, there's a variable star. If you want like a red star, there's one of those. So the good news is gravity doesn't care how much light you're emitting, and we're really good at detecting the gravity of close-by things. So if you even remember, the discovery of Neptune was based on its gravitational perturbations on Uranus. So if there was like a Nerebu dark star out there that was coming for us, which was, just 10 to the 28th kilograms worth of stuff, we would definitely know about it. So I'll leave this here, and if the relationship in between temperature and color, you just want to kind of mess around with this. This is a really nice applet where you have a temperature slider, and then it shows you what the perception of that star might be. So 7,000 is when you start getting into white hot and blue hot, and then lower temperatures you start getting like red hot, so on. And some of these things for scale is that, like, I don't know, the hottest your oven filament can be might put you at like barely visible red. Okay. So this was the first idea behind stellar classification, and for about 60 years, people very diligently looked at stars and tried to classify them before really knowing this temperature trick. So our legacy stellar classification scheme is historical and antiquated and kind of dumb, honestly. But there's so much work behind it, and it's so hard to like purge astronomy of historical relics that we have to learn this. So it's better to just have you guys learn it by telling the story behind the spectra classification. So people classified stars by spectra. They didn't really understand temperature until one of these people figured it out. All of this work and a lot of later work happened at Harvard. This is the stellar classification group at Harvard circa, I think, probably like 1910 or so. Do you guys notice anything kind of weird about this group of people? Yes, and there's this man, Edward Pickering. Any guesses about why that was? He probably may have been. He definitely looks kind of creepy to me, but I'll reserve judgment on that. Harvard in 1880 to 1940 or so would pay its employees on the following scale. So if you were a professor, you made a professor salary. If you were a technician in a laboratory, you made a laboratory technician salary. If you were a custodian, you would make a custodian salary. If you were male. If you're female, they just assumed that everybody was in the secretarial pool and there was a single female wage. Therefore, Edward Pickering, on a low budget, was able to assemble every single female astrophysicist and pay them an absurdly small amount and classify almost 500,000 stars. So I think everybody in this picture either is on their way to getting or has a bachelor's degree in math or physics or astronomy. And I don't know if it was like the camaraderie or what, but actually our modern understanding of stellar astrophysics basically is from this group. And it actually really doesn't have much to do with Edward Pickering. He was just the one person who they would actually fund. So basically all of these people with, some of them PhDs in astrophysics got like a quarter a day or something. I don't know. Some absolutely ridiculous wage. But there was like a machine. What would happen is you'd get photographic plates and spectra, and you would just churn out intensity diagrams. And the real question is, how on earth do these spectra tell you about what's going on inside the star? Because I showed you some pretty pictures, but this is what a real stellar spectrum looks like. Actually, this is a galactic spectrum, but it's not remarkably different. Does this look like that pretty smooth Blackbody curve with a color code on it that lets you know exactly? So this is what happens: is you break the light up with a prism, you shine it on a photographic plate. I see some dark dips, and then I see some bright patches, and I would draw out the squiggle. So these computers would draw out the squiggle, and then they would classify this star. If at some point you run across the HD catalogs, there's some stars HD blah 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 blah. That's this catalog, this group of people's catalog. And people basically started down kind of the wrong path, and were trying to classify these stars based on the squiggles and the bumps and the dips, which is exactly the thing that we now know you should ignore to get the correct answer, which is really you want to classify them based on temperature. So these are some real stellar spectra, and these are the actual spectra, and these are the associated intensity diagrams. And we'll get to it later, but you see that these squiggles are pretty compelling, is that the dips all seem to occur in the same spot. So they do seem to tell you something about what's going on. But then you can also see the broad part of the Blackbody spectrum. So this star, this is blue light, this is red light. What kind of star would this be? What overall color would it be? red. So this is a nice red star. What about that star? At the top, the O5V star would definitely be blue, much more blue than red light. And these are the actual prism things that you would see. So one thing is, yeah, appreciate the fact that the weird gaps in the spectra are kind of like calling to you for demanding an explanation. But yeah. Yeah, the sun is a G5b star. So if you took our sunlight and broke it up in a prism, you would see something that looked like that or that. Yeah, so this OBAFGKM thing, this is the remnants of the original classification scheme that the Pickering group was trying to make work because they were obsessed with the spectra, and it went A through Z, basically. This one woman, Annie Jump Cannon, basically said, enough is enough. It's temperature, you idiots, and left us with this. So the stellar classification scheme that we use is a temperature-based one. The OBA, FG, K, and M are a legacy of an earlier attempt at a spectral line one, classifying based on how big the gaps are. But this is what we use. This is what all astronomers everywhere use, OBA, FG, K, M. O is the hottest at a surface temperature of about 40,000 degrees Kelvin at the hottest of the O stars, and M is the least, is the coolest visible light star. In fact, there are two more now that we get to infrared light and can see infrared light. But this is stellar classification. This is like the most important thing to have a mnemonic for. If you were to remember one bit of random memorization in this class, it's OBAFGKM, where O's are really hot stars. F's and G's are kind of medium hot stars, like 8,000 to 5,000 or so. And then M's are really cool stars at about 3,000, 2,700. The typical mnemonic, feel free to do whatever, is O be a fine girl or guy, depending on preference, kiss me. OBAFGKM. And we've added brown dwarfs since then, which come in two flavors, L and T. So you can add less tongue if you want. It's the standard mnemonic. Make your own, whatever works. Learn not to make eye contact with anybody when you say that, so you don't get fired. But this is it. This is like the thing. This is the equivalent of, in biology, order, phylum, class, family, kingdom, genus, species, and stuff like that. Kings play cards on fine green sheets. This is the thing. And this is our classification scheme. Okay. So won't do any practice with that, because once we get to the HR diagram, you'll be absolutely sick of practice, and we'll use it a lot. But any questions about this? Yeah. Yeah. I thought it was like an indie band name, but yeah. Indie, yeah. Yeah, it's like a anagram for something really weird. But yeah, those are named. Personally classified like 400,000 stars. This is like the Terminator of stellar classification, circa 1900. No, it was originally A, B, C, D, E, F, G, da 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 da. And what A means is the A stars have the biggest dip there, and the B stars have the second biggest dips there. There were C stars and D stars and E stars and F stars. F stars had a slightly smaller dip. And as you see the O stars and the M stars, yeah. And she actually threw away a whole bunch of them. 2/3 of the old classification schemes were just tossed because it was like totally frivolous, and this is good enough. Okay. Further, they get subdivided in between 1 through 9 or something like that. So an O5 would be slightly cooler than an O3, and a B0 would be hotter than a B2 or something like that. And that's good enough. So yeah, with the permutation of the letters is the only annoyance. It would be nice if people just said, stop, let's just go back to A through K or something. But it is what it is. Okay. So we forgive them for this because, I don't know, get to make up a new mnemonic if you'd like. But we do want to know about this spectrum gap thing, right? So these things have these notches cut into what are otherwise really beautiful Blackbody spectra. And this is a spectrum from the sun. So it's presented the way that, the whole spectrum would wrap around the classroom. So it just kind of cut off the way that a book reads, and this is the next line, and then the next line, and the next line, and the next line. So what do you think is causing the gaps in the spectrum? Yeah. So what do you need to know to have that correct theory of why the gaps are in the spectrum? Yeah, which now that Professor Wick isn't in the room, chemistry is just applied quantum mechanics. So it's really quantum theory, which didn't come along until 1910, 1920. So we really forgive these poor people who are working in 1880, 1890, in kind of a pre-quantum world for beating their heads into this problem of the spectral gaps. And in fact, one of them, later person in this group, I don't know if she's in this picture, was the first person to successfully apply quantum theory to the structure of stars. Another, you just bag on Harvard all day. Celia Payne, at that point, was the first person to get a PhD in astrophysics from Radcliffe College. You guys know what Radcliffe College is? It's like the girls' school that was attached to Harvard. She actually really has a PhD from Harvard, but they didn't award it to her, so it's from Radcliffe instead. But she took Schrodinger's quantum theory and successfully applied it to stars using the spectral lines, saying that, listen, this thing's made out of 75% hydrogen, about 25% helium. That's what these relative abundances and gaps are, and therefore, we have this groundwork laid for the person to figure out that they're actually powered by fusion. So this requires quantum theory. So the idea that elements only absorb or emit certain types, their favorite elements of light, and applied that to stars. So that was a 20th century kind of thing. So you need to know a little bit about how quantum mechanics works, which is, it sounds very like kind of off-putting, like, oh my God, we've got to learn quantum mechanics. But it's really the idea that when you get like deep down into the nitty-gritty of it, is that electrons and protons are not, like your chemistry book might suggest, little green balls, billiard balls that whiz through the universe. There is not a particle theory of matter when you get down to it. It's a wave theory. And electrons are actually kind of like wave-like. There's a probability field of electrons flying through space. They're waves. They're like light. Light is a wave. They're delocalized. And so they have to do wave things. So for instance, a very normal wave, like the standing wave that happens if you pluck a guitar string, has to obey certain conditions. So the entire reason musical instruments work is because this guitar string is bound at the nut and at the bridge and at the nut, and it can't wiggle. So this end is fixed and that end is fixed. Because those two ends are fixed, the only allowable ways for the string to wiggle are like that, fixed at both ends, like that, fixed at both ends with a node in the middle, like that, fixed at both ends with two nodes in the middle, and so on and so forth. And so you get musical intervals that sound nice to our ears, and if you have somebody pluck a guitar string and you look at all the frequency spectra, you see that there are peaks at multiples. So this is music. But sensible, you guys know all this. So if somebody's playing a flute and you looked at the different frequencies, you'd see the exact same thing. That is exactly a Fourier transformation. And this is not that. I imagine this person would have much tighter frequency peaks on their playing, I think. So because electrons and protons are waves too, they actually also need to do this. And if you look at an atom, what you have is a proton sitting at the center. We don't really care about that. But then for hydrogen, at least, we have one electron hanging out around it. And the wave function, the so-called packet that describes how the electron is distributed in space, it can't have any like breaks or kinks in it. So it has to have, just like this thing does. Now imagine that you're just taking this wave and wrapping it around on itself so that the ends have to agree with it. One end has to agree with the other end. Is that we have one wavelength, two wavelengths, three wavelengths. And we can't have anything in between. So you actually, like you have discrete frequencies in a musical instrument, you actually have discrete frequencies in a hydrogen atom or a sodium atom or something like that. And you can't just jiggle the electron at whatever frequency you please. You have to get it from one node to the next node. excellent question. So if I went back to the molten peaks of metal, and the answer for you is no, you still can't win my $1,000. But is there some condition where I can actually see this, right? Because this is indicating to me that just like every musical instrument has its own sound, like every atom should have its own spectrum, which is exactly true, is there is a way to do that, but you kind of need a little bit of a condition, is the gas cannot, well, I said it, it's got to be a gas, it's got to be diffuse. So you can't have a big lumpy solid where all the atoms are bashing into each other and ruining it. So you have to have a very diffuse gas if you're going to see this quantum behavior. But absolutely you can. So in fact, this is the way of determining what's actually in stars, because otherwise we were totally sunk, is that this is the spectrum of hydrogen. If you take a gas of hydrogen and you beat it up with a current, and then you break that light up with a prism, you'll see individual wavelengths of light, right? So just a couple of them. And these individual wavelengths of light are completely characteristic of hydrogen and nothing else. And for helium, it would be helium and nothing else, and sodium, sodium and nothing else. And Dr. Gaporskin looked at the spectrum of the sun and identified what these were, and then used it to come up with a model of what it was actually made out of. But it's true that every element has its own particular fingerprint. So this is actually like fingerprints. Okay. And so these are the famous ones. So this is the sodium doublet. We don't really care about that in stars. Weirdly, this calcium set of buckets is really important. And then there's everybody's favorite, there's titanium oxide bands. So they're molecules in the surface of really, really cold stars. Is that 650 is hydrogen. It's a very famous wavelength. So hydrogen, 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 all the way down. Okay. You'll be shocked to learn that all stars contain hydrogen. That's what this is saying. Except I don't see it there. So the question is, why don't I see it in the really, really cold and really, really hot stars? They are made of hydrogen. The hydrogen itself. So what I would suggest is maybe looking at this, and let's say that if I'm at a really, really cold temperature, really cold, like 2,000 degrees Kelvin, maybe I don't have enough energy to knock this electron around. So I actually need two conditions to see the hydrogen spectrum. One is that it needs to be in kind of a diffuse gas, right? So nothing else is bumping into it and messing this up. The second thing is I need to have enough energy to be able to excite this electron into its second and its third energy state. So in fact, there is absolutely hydrogen in these stars. It's just I don't have enough thermal energy because they're too cold, so I'm not actually knocking that electron around. In the case of the O stars, it's at 40,000 degrees, so I actually have so much energy, I actually have plasma at my surface. So absolutely. Yeah. Yeah, photons don't have mass, but they can they have momentum. And if you've ever seen one of these, like it looks like a light bulb, and there's like a white painted and a dark painted side, and then sunlight actually pushes the thing around in a circle. I can look it up when we break. So photons absolutely carry momentum, even though they don't have mass. So there's actually a space travel scheme where you have a solar sail where sunlight actually just beats into the solar sail and imparts momentum to the spacecraft. So to get something moving at an appreciable rate, though, the solar sail's got to be like the size of California, so they're not, practically speaking, very useful. Okay. So in summary, and this is kind of a lot, but you can make light in two ways. This is the Blackbody spectrum, and the Blackbody spectrum is generally in a solid, and it tells you the temperature and the temperature only. So the Blackbody spectrum carries no information about the constituents of whatever. And then secondly, what we're calling the emission spectrum, where you have a big diffuse gas of atoms, and then you either let them absorb or emit light. They will only do so at their favorite wavelengths, And they're absolutely fingerprints, so this would be a sodium spectrum and a neon and a helium spectrum. And that you can totally identify something with. And what's happening in a star is I've got a black body component, the really hot core of the star, and it's surrounded by a gas of less dense material. So I've got two of these things happening at once. So you can think about this as there are two ways of making sound out of a musical instrument. Is you could play it or you could throw it down the stairs. So. Okay, so specifically what's going on in stars, and we talked about emitting and seeing bright flashes from, for instance, hydrogen's favorite wavelength. Why do I see gaps here? Well, what's actually happening is the light being emitted by the core of the star, the black body, is passing through the gas, and the gas is absorbing its favorite wavelengths of light instead of emitting them. So it's actually kind of eating them out of the spectrum and shooting them off in some random direction. So you don't see it. So in fact, what you're seeing here is that the sun was totally emitting this light at its surface because it's a black body and it emits everything. But then I think this might be the sodium doublet. So there's sodium in the sun, and the sodium in the sun is absorbing that particular type of wavelength because it's its favorite. It's one of sodium's wavelengths and depleting it. And collectively, these are what are called Kirchhoff's laws of spectroscopy. Where you'd see a continuous spectrum if it was just a black body, like a lump of tungsten at a high temperature. If it was a hot gas being beaten up by some energy source, you would see the emission line spectrum. And if you combine those, you put the cool gas in front of the hot black body. What the cool gas does is it absorbs its favorite wavelengths of light. And you can really think about this as d plus d equals d. Right? So this is what the center of the star is doing. And then the cold cloud of gas is taking out its favorite wavelengths and depleting them from the spectrum. Okay. Questions about that? Okay. So just pointing out that all of this is happening in the photosphere. And when I say cold, I mean 5,800 degrees. That's cold, I guess. Cold enough to be a gas with neutral atoms in it instead of ionized atoms. So, okay. You guys believe me?